Here is an example. In this example, he's asking us to convert an ordinary two-winding transformer into a auto transformer. So the rating of the transformer is given, which is a 60 volt ampere, and it is 120 by 10 volt, 60 hertz. Okay, whenever we are going to the market to buy a transformer, usually you see these three values: rating of the transformer, like 100 kVA, 200 kVA, 100 MVA, like that, and the voltage rating, like 230 kV by 33.5 kV, something like that, and the frequency, either 50 hertz or 60 hertz. Now the transformer rating is always in either kVA or VA. I mean, he will give you only value of S rating, not the P, because the transformers are always rated in apparent power, since the manufacturer doesn't know the power factor of the load when he is building the transformer. So even if you look at the transformer in your neighborhood or behind your home, those transformers are rated around 100 kVA. So even if you look at your home, see, in the winter time when you turn on your heater, the heater is purely resistive load. Okay, so power factor is unity there. In the summertime, you're going to turn on your AC. AC usually is a lagging power factor, poor power factor, like 0.7, 0.75, less than 0.8. So that's a lagging power factor. And depending upon whatever the other loads you're using, most of the time our power factor is going to be lagging, but it is varying with respect to the load what we are using in our home. So that is the reason usually manufacturer rate the transformer in kVA or volt ampere. So now here he want us to make this as a 120 by 130 step up transformer. I will also try for 130 by 120 step down. So step up transformer, our primary must have 120 volts. So I'm going to keep the primary winding as it is, plus and minus 120. Now my output must be 130 volts. So here is my output, here is my another winding. So what I'm going to do, the orientation, I'm going to keep it in the same direction. Okay, so say for this example, that's X and Y, I kept my X right here. Okay, this is my Y. Now according to the dot convention, oh, before going to the dot convention, sorry, I need to tell you one important point. Based on the rating, can we find the current passing through each winding, the capability of current carrying capacity of each winding? So this I1 and I2, okay, I1 must be 60 over 120, which is 0.5 ampere. So the primary winding, so let me take this as N1 and N2. N1 can handle up to 0.5 amperes. Same way, I2 equal to 60 over 10. So S over V will give you, S is nothing but V times I conjugate. So based on that, I found I, which is 60 divided by 10, 6 ampere. Okay, I conjugate is nothing but, if you have I equal to 3 plus J4, I conjugate is nothing but 3 minus J4. Here I'm using only real number, so need not to worry about the conjugate. Okay, that's the reason not considered conjugate there. So according to our previous calculations, I can see this N1 can handle up to 0.5 amperes. So this winding can handle up to 0.5 amperes, and N2 can handle up to 6 amperes. Okay, we'll find the current direction in a second. Okay, now the 0.5 ampere is entering the dot, so the dotted terminal must be positive. So I will end up having 10 volt there. What is the total voltage? The total voltage must be here 120 plus 10, which is 130 volt. Okay, now when it comes to the current direction, here this is the secondary winding of transformer. Current supposed to leave the positive terminal, so current is going to go in this direction. So current supposed to leave this positive terminal, or you can say actually current supposed to go in this direction. How much is that current? That current must be 6 ampere. Why not 5.5? Why not 6.5? Because the maximum current this N2 can handle is 6 amperes. So for sure the maximum current I can take is 6 only. It could be 5 amperes too, but since it can carry 6 amperes, I'm taking that as 6 amperes. So if 6 amperes is passing through this, how much current is flowing here, entering here? So this is 6 leaving, 0.5 is also leaving, so 6.5 ampere. So now if you consider this ideal transformer, 6.5 ampere is entering with 120 volts. So the rating of the transformer is 120 times 6.5, or you can say 130 times 6. Both of them are same, so that value is 780. So a 60 volt ampere ordinary transformer is modified into a 780 volt ampere auto transformer. See, the rating of the transformer is increased enormously. That is the advantage. So a smaller size transformer can carry huge amount of power. The only disadvantage is the primary and secondary winding has common connection. So I mean there is electrical connection. So if something goes wrong on one side of the transformer, that will transfer to the other side. It will damage the whole equipment. That is the reason we don't use auto transformer widely. So out of this 780 volt ampere, how much is transferred by induction and how much is transferred through conduction? Induction and conduction is nothing but, if you look at the ordinary transformer, here the energy is transferred induction principle only. That means there is no electrical connection here, so it has to induce, the energy has to induce in the second coil. That's how it will transfer it to the load. So the induction principle, so whenever we transfer ordinary transformer into auto transformer, the energy transferred through induction principle is always 60 volt ampere. The remaining 720 volt ampere is transferred through conduction principle. Okay, now the same example, I'm going to convert this into a step down transformer. See how it's going to work. So here is a step down transformer. In the previous case, I have N1 connected to the primary. Now this N1 is connected on the secondary side. So obviously I'm going to call this as N2, number of turns on the secondary side, number of turns on the primary side, N1 here. Now this coil, so the voltage drop across this must be 10 volt. Okay, the remaining 120 volt is going to appear there. So the current is entering the dot, so the dotted terminal must be positive. That is the working principle. Okay, now how much current this can handle? Whatever the current is going out, this can handle up to only 0.5 ampere. This can handle up to how much? 6 ampere. Okay, so the current coming here must be 6 ampere, and the current going out here must be 6.5 ampere. I mean, you can clearly see the current is entering the dotted terminal must be positive, and current has to leave that positive terminal. So that's how I calculated. Okay, so out of 6.5 is going to come over there, 5.5 is going to go through N2, 6 amperes is going over there. So the rating S is 130 times 6, or same as 120 times 6.5. Okay, so the same transformer I can use it as a step up transformer or step down transformer, depending upon which voltage is the higher, which one is the lower. What is the transformation ratio for this? N equal to, always, what is the total winding on the secondary side? N1 plus N2 divided by N2. Okay, so if you look at, the voltage, So I have 120 volts there, so N1 must be a lot bigger than N2. If I look at N1 to N2 ratio here, 120 by 10, so this is 12:1. So here this is 12, this is 1. So this transformation ratio or transformer ratio is 12 plus 1 over 1. So here it is 13. This is 12 and this is 1. So transformer ratio N equal to N2 12 over 12 plus 1. Okay, so that is 12 by 13. Okay, I'll stop this video here. In the next video, I'm going to solve another example based on the auto transformer. Thank you.